we can move on to gated recurrent neural networks. So I think by now you have noticed that whenever I want to introduce a method, I try to introduce it in terms of applications. So we introduce convolutional neural networks, recursive neural networks, and different types of models in the context of application. So our application here is document classification. So for this paper, it's nice because I'm going to introduce gated recurrent neural networks, and we're going to see a glimpse of attention. So what is the idea? What is the big picture here? We know that words are going to form sentences. So a sentence is a sequence of words. And we know that documents are formed by sentences. So words form sentences, sentences form a document. So that's the big picture about language, and there is nothing wrong with it. And we can even go at a lower level. Characters form words. And we're going to see that in the next slide when characters are forming words. But there is nothing wrong with this statement. Words form sentences, sentences form a document. So let's leverage that, and let's write a model that is trying to leverage it. You have a document, and you want to represent your document by a single vector, v. Once you know v, then you can do a softmax, and then you can do your classification. Then your problem is solved. But then each document is formed by a bunch of sentences. Sentence 1, sentence 2, up until sentence L. And L could change from one document to the next document. So it's a variable length sequence. And each sentence is going to get formed by words. So the second sentence is going to have W21, W22 up until W2T. And then T can also change from one sentence to the next sentence. The same thing is going to happen for S3, S4, etc. So now we want to write a model for it. Don't worry about these components, what's happening here or what is happening here. I'm going to go through it in more details right now. So what type of a model are we going to use? We are going to use a GRU. It's a gated recurrent unit. So we're going to have an RNN with a nice activation function, with a gated activation function. And this is exactly what you're seeing here. It's a recurrent neural network. You have the previous hidden state, the current word, they combine to give you the current hidden state, and then the same pattern is going to repeat. And then you are sharing parameters. So this parameter here and this parameter here are shared with the parameters here and the next one, the parameter here and here. They are shared. They're the same parameters. And I said you're going to have a nice activation function. And that's called, you're going to need two gates. You're going to need a reset gate, and you're going to need an update gate. What is the update gate doing? You want to go from the previous hidden state to the next hidden state. So this is where the information is getting accumulated. So you want to go from the previous to the current. Z is going to tell you how much of the previous state you're going to keep. So you're going to keep 1 minus Z of that, the previous state, and how much of the new information are you going to pay attention to? How much of the new information are you going to keep? So that's the update gate. If Z is 1, you're ignoring the history because this is going to end up being 0. And then you're paying a lot of weight. You're putting a lot of weight on the current information that you just got. But what is that information? And how do you set Z? Z is going to be sentence dependent. So it's not a single number, and that's why it is smart. So each data point that goes in, it's going to have its own Z, okay? Each sentence that goes in, it's going to have its own Z. Actually, each word that goes in, it's going to have its own Z. And how does it happen? This is a new word, or this could be a new sentence. So this model is for both words and sentences. So you're going to use the same model down here and up there. A new word or a new sentence goes in, you're going to multiply it by a bunch of weights. It's a linear combination. The previous hidden state goes in. So this is the previous hidden state. This is the current information, X. You multiply that by a weight matrix. So these are the parameters that you're going to learn. And you add some bias. But this is a number from negative infinity to positive infinity. We want to have a number from 0 to 1. So you're going to push it through a sigmoid function. and that's going to squash it into 0 and 1. Okay, this is your update gate. And what is the new information? The new information, again, it's very similar to what you have up there. It's going to do this. There is going to be X at the current time that goes in. Forget about R for now. Then there is the previous information that is going in. You multiply them by weights. You add a bias. You push it through a nonlinearity. And then that's going to give you the new state. And Z is going to tell you how much of that new state you're keeping. But there is also another point where you can reset the information. So even in H tilde, you're going to reset the information that you want to keep. So there are two versions of this gated recurrent unit. One is that you first multiply by a matrix, and then you decide to keep the information. Or equivalently, you can first multiply HT minus 1 by RT, and then multiply by a matrix. So you can switch the roles of RT and UH. There are two versions of it. I think the one that multiplies HT minus 1 by RT is more popular. They're very close in terms of performance, but empirically, that one is doing better. And when we go towards covering speech recognition, I'm going to go through a paper studying all of these types of recurrent neural networks and telling you which one is better, what type of a configuration. So that's a systematic study. But for now, this is the model that we're going to use. And if you think about it, RT is operating on HT minus 1. So this is how much of HT minus 1 you're resetting. And ZT is operating on H tilde. So this is happening at time t. This is happening at the previous time. So you're resetting some of the information, and RT is very similar to ZT, having its own parameters. Any questions so far?
So that's the left to right part of this diagram. But then what about the different arrow that's right above it going from right to left?
So that's a great question. So what you're going to do then is just reverse your time, and then it's going to let you go from right to left. So it's the same model, but now you're going from time capital T to time 0 or to time 1.
And then,
so your for loop is just going to be a backward for loop.
And then you concatenate those and push those forward?
Yes, so this operation that you see is concatenation.
Okay.
And that's what I'm going to cover right now. So you have your words. This is your word. The first step is always encoding it. So you're going to have word embedding. You multiply your word embedding matrix by your one hot encoded words. And this WE, you can either initialize it randomly if you have enough data, or you can initialize it using word2vec or a glove model. But then it's going to give you X, and this X is the one that is going to go through the GRU. And as you said, there is going to be a forward GRU, and then you're going from, your time is going to get indexed from 1 up until capital T. And you can have a backward GRU, where your time is getting indexed from capital T to 1. So it's going in the backward route. So this one has its own parameters. This one has its own parameters. These are the parameters of your model: WZ, UZ, BZ, WH, UH, BH, WR, UR, BR, and then you have forward weights, and then you have backward weights. And as you said, you're going to concatenate them. You have a vector for the forward, you have a vector for the backward at state capital T. You're just going to concatenate them, and that's going to give you a vector having twice the size of each one of these. So far, so good. That's a forward, backward GRU. So we covered up until this point, and exactly the same thing is going to happen up there. It's still a GRU, but then that one is operating on the sentence level. So now let's introduce these attention, because in the end, you want to combine these words into a single vector for your sentence. So your sentence is going to be a linear combination of these vectors with some parameters, alpha, alpha to 1, alpha to 2, etc. So let's see how we're going to do it. We are going to take H. First, we are going to correct the dimension. We are going to push it through a nonlinearity, and that's going to give you a vector, UIT. So for each one of these, now you have a vector. But then you want to know what should be the weight when you're combining these HITs together. See, this SI is just a linear combination of these H. Now you want to know what is the most important word in this sentence, or what are the most important words. Maybe a couple of them are the most important ones. And these are the importance weights that you're associating to each word in that sentence. So this is how much attention you're paying to this word in the sentence. And we know that we have a fixed budget of 1. This is our attention span. We have only 1 attention unit, and we want to spread it across our words in the sentence. And how are we going to do it? We need these numbers to be from 0 to 1 because that's our attention. Our attention cannot be bigger than 1. And then we want them to add up to 1. And whenever you have this property, there is a softmax behind the scene. So we know that there is going to be a softmax. Perfect. But now these vectors have a dimension. They are vectors. We want to turn them into scalars. And how do we usually do it? We turn a vector into a scalar by dot product. So a lot of deep learning, we can think of it just as dot products. And that's what we're going to do. The question is, what are you going to dot product with? What is UW? This is a parameter in your model. And you can think of it, this is an interpretation. Mathematically, this is just a parameter. But in terms of interpretation, you can think of it as a context word, or you can think of it as a query. We can associate with it a meaning. And by query, I mean, it's just a question. You are asking from this sentence, what is the most informative word in this sentence? We can think of it that way. But its role is to give you numbers mathematically. Once you have those numbers, you have a softmax. These are going to add up to 1. And your sentence is a linear combination of your words. So that is what we just covered here. Words are going to form our sentences. And this is how they're going to form your sentences. You have a forward GRU, you have a backward GRU, you concatenate the states, and then you're going to linearly combine the states to give you your sentence. So is this clear?
How do we ensure that the dimensions are compatible here? Is the WW, the capital W sub W
Yes,
always?
so this is going to take care of that. So you set the dimension of UW, and then all of these dimensions, these are the things that you are controlling. The dimension of your hidden unit, you set it yourself, and these are hyperparameters of the model.
But you don't know how many words there are per sentence, right?
But that doesn't matter. Why? Because in the end, you're going to end up with these alphas that are going to combine all of those words into a vector.
Yeah.
It's like max pooling or average pooling,
Yeah.
but now it's a weighted average pooling.
That makes perfect sense. And that S will always be the same size because we can control the size of H.
Yes.
Okay, perfect. Thank you.
What are we going to do next? Now we need to combine our sentences into a single vector. And the pattern is exactly the same as before. You're just renaming your input and hidden states. That's all. Let's see. How do we encode a sentence? You have these S's. How do you encode a document? So these are your sentences. Your document is going to be formed by a bunch of sentences. You're going to have a forward GRU. You're going to have a backward GRU. They're going to have their own parameters. Okay, perfect. You concatenate them. Then you're going to do the attention. You want to know what are these alphas. You're going to have a sentence query or sentence context vector that you're going to borrow. These are the parameters of your model. And you can interpret it as what is the most informative sentence in this document. Then V is just a linear combination of these concatenated vectors. And these alphas, they're going to add up to 1. You have an attention span of 1 or attention budget of 1, and you're spreading it across your vectors. Once you have V, you can do your document classification. Now the dimension of V could be different from the 5 classes that you're interested in. So you do the projection, you do your softmax. This is going to give you a probability distribution. Per each document in your data set, you're going to have a PD. Now you want to maximize the probability of the correct class, and J is going to pick out the correct class for you. So J is the correct label. This is coming from your training data. For training data, you know your document and you know its class. For instance, the class could be the second one. P is a vector, and then you're picking up the second entry of your vector and maximizing that.
This is the same thing as before, except before you had like the coefficient y, and that was just like essentially like an indicator variable, right? You were saying that's a one hot vector, so it's acting just to select a certain index, and this is a different way of writing the same notation.
Yes.
Okay.
So I want you to get used to these two types of thinking about it. One of them is a cross entropy loss, and one of them is a maximum likelihood loss, or your likelihood loss. They are equivalent. So what I'm writing here is a likelihood, or negative of the log of the likelihood. And what we saw before with one-hot vectors, that's just a cross entropy. And because one-hot vectors are one at a hot location and zero everywhere else, these two formulations are going to end up being the same. So what can you do? You can do sentiment estimation, you can do topic classification, and you can have different data sets, different number of classes, and different size for your data sets. So these are the ones that you can do exploratory data analysis on. The cool thing about attention mechanisms, or attention in general, is that you can visualize it. And this is awesome. You can visualize alphas, and let's say you have a sentence, and that sentence had the ground truth of the class being 4, and the prediction was 4 also. So the algorithm is doing the correct thing. It's not making a mistake there. But now you want to know which one of these sentences were the most important ones. So you can look at this red column here, and it turns out that this entry and this entry were the most important ones. This is another example. This entry here and this sentence here were the most important ones for predicting a very negative outcome and a relatively positive outcome. But then you can do it per sentence as well. For this sentence, which words are the most important ones for that prediction? The prediction here was negative, and it turns out that terrible was the most important word, and not here. Same thing here, amazing was the most important, or delicious was the most important for that Yelp review. So attention is very nice because you can visualize it and you can see what the network is thinking. So what did we do? We learned about recurrent neural networks with a particular activation, and this is our gated recurrent neural network. And we learned about attention a little bit.
I think there might be something that you're showing that we can't see. I think you just talked about an example, but I think that
So now, do you see it now?
no. I just see up to document classification. I don't see anything on the right side, and I think I'm not the only one.
I think something is wrong with Zoom. So how about now? Do you see
Yeah,
it?
I see it now.
So this is our data set. You can do exploratory data analysis on that data set. And each one of them have different number of classes and documents. And then you can have an example. The cool thing about attention is that you can visualize, for instance, for this prediction, what is the most important sentence for that prediction. And you can look at this column, where you have the most red, that's where the network is paying the most attention to. And you can have another example where your prediction is negative. This term here, this sentence, and this sentence here are the most important. They have the biggest alphas, but not only you can do it for sentences, you can do it for words. For instance, for this sentence, delicious and amazing for the other sentence are the most important ones. And here, terrible is the most important word, and not, etc. Any questions? So there is a question, how is the query context word selected? Is it a global learn parameter, or is it the word embedding at the position or something else? No, this is actually a global vector of parameters that you're going to learn. And it has a global meaning. It means what is the most informative word in this sentence, or what is the most informative sentence in this document. Okay, perfect. Any other questions?
Is there a general agreed upon best embedding, like for these first layers? Does everyone use one hot? Does everyone use glove? Or is it kind of just whatever your favorite flavor is?
So that depends on the size of your data. See, some of the data sets are smaller, some of them are bigger.
Mm-hmm.
For the smaller ones, probably starting with a word vector initialized by glove is probably going to give you better results. So you're doing some transfer learning there for some of your parameters. But the bigger data sets, there is probably enough data that even if you initialize this from random locations, they're going to end up in the correct location. Okay?
Yeah.
Any other questions?
Yeah, I have one. Would you mind briefly going over which parameters are being shared between the words? I know you said that each word will have its own Z and also, I believe, attention.
Yes. So what is being shared from each hidden state and each input word, or in each input sentence, depending on where you are in this graph, you're going to have parameters. You're going to have WZ here, WH, WR. Actually, sorry, W is here. You're going to have WZ, WH, WR for your X's. You're going to have UZ, UH, UR here for this arrow. And you're going to combine them. But then from this point to the next point, from this time step to the next time step, you're going to use the same parameters. So it's going to be the same U's and the same W's as the previous time step. Up until the end, it's going to be the same parameters. And that's how you're sharing parameters. So that's for the forward. For the backward, it's the same story. You're going to have W's here, U's here, but then from this time step to the next one, you're going to copy and paste the same parameters. Does that answer your question?
Yeah, definitely. And then did we say that we have a different attention for each word in the dataset?
Yes, this is going to be different because you have different data sets going in. See, these are functions. This alpha IT is a function of U. U is a function of your previous time step. It's a function of H. And H is a function of the previous time step and X. So each new data, each new word that goes in, it's going to change your alphas. And this is exactly what we are seeing here. These are two different predictions, two different data, and each one is having its own attention pattern. It is because we are having a function here, not because we have a lot of parameters. We are very efficient in terms of parameters, but we have different alphas. I think we are 1 minute over time. For those of you who want to leave, you can leave. And for those of you who want to stay and ask questions, I'll be around. Yes, so Teddy is right. The alphas are not learned, they are computed each time. So they depend on what is being learned are these W's and U's and B's. But alpha is a function of your input. Yeah, this is smart. This is really smart. And that's why these recurrent neural networks, LSTMs, GRUs are powerful, because these weights that you're putting here are data dependent. So not many people take that into account, but these are powerful because they're data dependent. They are functions of your data.
Is this a bi LSTM?
Say it again.
Is this what they call, I think it's bidirectional LSTM?
This is bidirectional GRU. So GRU's gated recurrent units is a simplified version of LSTMs. So they have less parameters.
Okay.
And they have less gates. This one has only 2 gates, but an LSTM is going to have 3 gates. You're going to have a forget gate, input gate, output gate.
Okay.
But they belong to the same family.
Yeah.
They belong to the family of gated.
Yeah.
And they have the same performance or similar performance. Okay, I started with GRUs because they have less parameters and they are easier to explain. Not that LSTMs are difficult to explain, but...
Are we going to do LSTMs next?
Yes, it's going to be next session on Friday.
Okay. Yeah, because I've seen those before, and we kind of just breezed past them in the NLP class I took in the fall. So
these ones, LSTMs, GRUs, etc., they have more applications when we do speech recognition. So I'm going to go into more details there.
Interesting.
For now, I wanted to say that for natural language processing, you can use different types of models. You can use convolutional neural networks, you can use recurrent neural networks, you can use recursive neural networks, you can use attention models. And this is the first time that you're seeing attention.
Yeah.
And we're going to keep updating that.
Yeah, attention comes back all over the place.
Yes.
Cool. Thank you.
Yeah. Any other questions?
Yeah, I just wanted to verify that I understand. The part of the gates are just a value that tell you how much to forget or to reset. So they are also functions that relates to the previous values, the previous sectors, I suppose.
Exactly, yes.
Cool.
So Z is going to tell you how much of the previous information to keep.
So they are similar to the attention in the sense that we calculate them every time rather than learn.
Yes, you can think of it exactly like that. So you can think of these gates as attentions also. How much attention do you pay to the previous time step, and how much attention do you pay to current information that you just observed? Because a new information came in, XD came in, and how much attention do you want to pay to that? So yeah, you can think of these gates as attentions as well, if that's how you want to think about it.
Okay, that makes a lot of sense. So we have, for the forward pass, we have one W from H21 to H22, and then one W from W22 to H22. That's
Yes,
correct?
yes.
Okay. And then we have the same, sorry, not the same, but we also have two different Ws for the backward pass.
Exactly. So you're going to have your own W's and U's for the forward pass, and then different types of W's and U's for the backward path.
And then we have four W's for the sentences, or are they shared?
So the same thing here. You have different W's and U's here. These are different from the ones that you use for your words.
Okay, that makes a lot of sense. Thank you.
So what is being shared is from one time step to the next one. So nothing is being shared from this. So this is vertically, nothing is being shared, but horizontally, things are being shared in this figure.
Okay, that makes sense.
So you have parameter sharing over time. Okay. Any other questions?
So there's been a lot of debate around attention is not explanation and attention is explanation. So can we still call like whatever word has a higher attention? Can we still say that a model is paying more or a model is finding that important for a prediction?
I think so, yes. And this is an example of trying to make sense of those attentions.
Mm-hmm. I mean, there was a paper that I read called "Attention is Not Explanation," and in there they made some like they did some experiments where they um, changed the values of the attention, and still the prediction was same. And they attributed to the fact, they attributed it to the fact that attention is very convoluted, and like we cannot say that even if a word has higher attention, it might be important for a particular prediction.
Probably, but that depends on the model.
Yeah.
So
True.
sometimes you're doing multiple attention mechanisms and you're stacking them on top of each other.
Yeah, like
For those ones, maybe it's more difficult to interpret them.
Right.
But here, this is a simple model. So you have one attention for your sentences and you have a bunch of attentions for your words. I would say that for this model, this you could think of this as explanation. But at the same time, there is some nonlinearity going on here. This is not actually your sentence. It is whatever information that is being accumulated in your sentence up until that point.
Yeah.
So yes, you're right. It's hard to interpret them, but at least for these two examples, they make sense.
I was thinking that it might be possible that some vector in, say, the S1, S2, SL, maybe some vector is upweighting. So it might be that because of some multiplication there, it is upweighting some attention which was downweighted before. So that's what I was thinking in this sort of model. I mean, it definitely makes sense in transformers because there are so many attention layers in encoders and decoders. But I was thinking, like in a model, in a simpler model like this, is it possible that some weight after this sentence encoder might be upweighting some vector which was downweighted, and it might be difficult to understand after that?
Yes, exactly. That's exactly what I mentioned. Once this sentence goes through these nonlinearities of your recurrent neural network, then it's not the same sentence anymore. It's just a representation of it. It
Yeah.
has some weights and biases, so it's messed up.
Mhm.
So yes, this alpha doesn't directly correspond to S1.
Right.
Or this other alpha, it has other S's in it, and then you're right. Maybe one of these sentences is being downweighted because of these nonlinearities.
Yeah, maybe. Yeah. Okay.
So, but these neural networks are hard to interpret. There are some ways of interpreting them, and I covered them in part 1 of the course.
Okay.
But yes, this is just an attempt at explaining that.
Yeah. Did we talk about Lime in part 1?
Yes.
Oh, okay.
So those types of methods we cover in part 1.
Right. Okay. Yeah. Thank you.
Yeah, you're welcome.
Okay.